Today we will going to continue chapter 9 and sequence. Okay. 9.1 sequence. So what is a sequence? A sequence is defined as a function whose domain is in the set of positive integers. Sequence is defined as the function whose domain is the set of positive integers. One, for example, 1, 2, 3, 4. Okay, continue n. So then the domain is 1, 2, 3, 4, 5, 6, 7 until n, and its corresponding term is a1, a2, a3, continue an. Okay, so we call a1, a2, an are the terms of the sequence. Okay, so an an is it's going to be the nth term. That makes sense, right? Okay, so let's look at an example. 1, 3, 5, 7, 9, 11, 13, continue. So suppose the first term is a1 and the second term is 3. So second term a1 equals 1, second term is 3. So can anyone tell me what is the nth term an? What is the nth term? So can anyone tell me what the nth term is?
I think it's going to be the first term plus n minus 1 times the difference between the numbers.
Very good. Okay, very good. So the nth term is going to be, thank you, Lacey. The nth term is going to be, the first term is 1 plus, okay, and n minus 1 times the difference between each one is 2, and there's going to be 2n minus 1. Okay, that's for nth term. Okay, so we can see that an minus 1, the difference between two terms is a common difference, d, and for this one, especially for this one, okay, an minus 1 equals d equals 2. Sometimes equals another number, but they all have a common difference. This kind of sequence, we call it arithmetic sequence. Does it have a okay, so we also have the s equals the first one is a1 2n minus 1, second one 2n minus 1. Okay, so we got s the first n plus 1, okay, equals 1 plus, if you just have Sn, okay, so Sn is the first term plus the last term multiplied by n divided by 2. Okay, so this is arithmetic sequence. Next one, if we have another sequence, for example, 2, 4, 8, 16, 32, 64, 128. So continue, and then this is A1 is 2, okay, and A2 is 4, A3 is 8, A4 is 16. So now, what about the nth term here? Can anyone tell me what is the nth term here?
Two to the n.
2 to the nth power. Very good. So for example, the first one is 2 to the first, second is 2 square, third one is 2 cube, fourth one is 2 fourth, and continue. The nth term is 2 to the power n. Okay. So this one will have the two consecutive terms, an over an minus 1. The next one over the current one. So next to each other, they have a common ratio equals r. So this sequence, we call it geometric sequence. Okay. So geometric sequence have the s, the summation equals 1 minus r, a1 times 1 minus r to power m. Okay. Let's look at an example. Okay. Write the first 5 terms of the sequence. For example, an equals 3 to the power n. So now I would like to call a student to help me with this. Thea, could you please tell me what is A1? A2? A3? Very good. A4? So you can just say 3 to the power 4, right?
Yeah.
Okay. So A5? 3 to the power 5. Perfect. Okay. A3 is 81. And this is 243. Okay. So in your homework, I think you do have a problem like this. Give you a function of an finding the first 5 terms. Okay. The second one. Suppose an equals 10 plus 2 over n plus 6 over n squared. Okay. So A1. Alright. Zhijian, could you please tell me what is A1? Okay, A2? Okay. 12 and a half. I can give you the final answer. So A3. That's 34 over 3.
A4 is 10 plus 2 over 4 plus 6 over 16.
Okay, that's 87 over 8. A5.
A5 is 10 plus 2 over 5 plus 6 over
Yes, okay, very good. So it's 266 over 25. Perfect. Thank you very much. And this is the second example of a sequence. Give you a sequence, give you a term, like a function of an, you find the limit of the sequence. Okay? And the next, so find the first 5 terms of the sequence. So next one, we're going to look at the limits of sequence. What's the limits of sequence? Which means I give you an, for example, this one. Give you an. Now when n goes to infinity, what is the an? Okay. So the limits of sequence is, definition is let L be a real number. So the limit of a sequence an is L, written as limit n goes to infinity, an equals L. Okay, so n goes to infinity, the term limit of the term equals L, and if for each sigma is bigger than 0, epsilon is bigger than 0, so there exists a m be 0 such that the an minus L is less than epsilon whenever n is bigger than m. So this means after a certain point, the limit between the difference between the n, the L, and an, the difference between them is smaller than a epsilon, a small number, okay, which means they're very close. After a certain point, they're close to each other and it's less than a small number, epsilon. Okay, so it means it's convergent to that point. It's the difference smaller, smaller, smaller. In the end, it will get the limit equals L. Okay, so if the limit L of a sequence exists, so if the limit exists, then the sequence converge to L. Okay, so let's look at several examples. First one, an equals 1 over 2n. Well, if n goes to infinity, you can look at limit n goes to infinity an, which equals limit n goes to infinity 1 over 2n. You know that this one equals 1 over infinity, this equals 0, right? So the limit goes to, is the L equals 0. Okay. Or even you have another one, for example, an equals n over 2 to power n. As n goes to infinity, we can tell that limit n goes to infinity, an equals limit n goes to infinity, n over 2 to power n. Well, this is the infinity over infinity form. Use L'Hopital's rule. You can get the limit n goes to infinity and 1 over 2n. Wait, it's not 1 over 2n, it's 1 over 2n ln 2. Okay, so then it's still infinity, so it's go to 0. Okay, that's how you find this the sequence of a limit. Okay, the limit of a sequence. Alright, so let's look at a example. I think we did this one before. Okay. First, let's look at an example first. an. Find the limits. Find the limits. An equals 1 plus 1 over n to power n. Okay. So find the limits. An equals 1 plus 1 over n to power n. What do we have before? We have limit x goes to infinity 1 plus 1 over x to power x. Can anyone tell me what's the limit of this one? Do you still remember how we got this? Whenever you see a power have an x, you take the ln, right? And then use L'Hopital's rule. Do you still remember what is the limit of this one? E, very good. Okay, it's E. Alright. So now the limit of limit n goes to infinity 1 plus 1 over n to power n also equals E. Okay. You may tell me, oh, n is not a here. N is integer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Y is an integer. But here x is like any number. It could be any real number. 1.1, 1.2, 1.3. For this one, x is continuous. For this one, n is not continuous. N is just the integers. But they do still converge to the same point as n or x goes to infinity. So this is based on one of our theorem. Okay. So let L be a real number. And let F be a function. Of a real variable such that limit x goes to infinity fx equals L. So in this one, x is a variable. X is continuous variable. Okay. And the limit of fx as x goes to infinity equals L. Now, if the an is a sequence such that fn equals an. So for this function here, fn equals an, the n is just the integers. But here, x is any real numbers, n is integers. Okay, so for every positive integer n, then the limit n goes to infinity, an also equals L. Okay. Even the x here is a continuous variable. Okay, 1, 1.1, 1.2, 1.3 continuous variable. And it goes to, they converges to L, x goes to infinity. Here we have the n is positive, n is just positive integers. 1, 2, 3, 4, 5, 6, and 8, 9, 10, you can goes to infinity integer numbers. But if they have the same function, you change that, they still converge to the same point. Because infinity, we're talking about infinity converge to the point, okay? Does that make sense, everyone? Yes? Okay. Alright, so show that sequence. Example. show that sequence an equals n squared over 2 to the power n minus 1 converge. Show this sequence converges. Okay, so how do we prove that? So now we only have a sequence. Okay, we cannot, I think here I cannot here of right here. Okay, right, this one here I should not use a L'Hopital's rule here because this n is not a continuous function, but we still can do it. Okay, so this one, it goes to 0. You still can use the this theorem to do it because n is not a continuous function. Okay, you have to change that into x first. All right, so consider function of a variable x goes to r. So consider how function f(x) equals x squared over 2 to the power x minus 1. You see, the n is a variable, a domain, but n is just all integers, 1, 2, 3, 4, 5, 6, 8. Okay, but x, here we change the n into x. X is a continuous function. The reason I change that into x because x is continuous, I can take the derivative. Okay, and limit x goes to infinity, x squared 2 to the power x minus 1. So this variable x is a continuous function. X is continuous and is differentiable, both top and bottom. Even x goes to infinity, this is going to be infinity or infinity form, and we can use L'Hopital's rule because f(x) is continuous function. Okay, both the top and the bottom are continuous. So now then I can use the L'Hopital's rule. But this one here, I said wrong here. Okay, if I have to do this, I have to change that. I have to do another thing. Do f(x) equals x over 2 to the power x. Then I have to use a L'Hopital's rule, prove that limit x goes to infinity, x to the power 2x, this one equals 0. I have to do this, then go back to prove that equals 0. Okay, I cannot take the derivative, use L'Hopital's rule on the n here because the n is not continuous right here. Okay, so now but it's not mathematically, I can just be more rigorous. Okay, so now x is continuous function, then I can take the derivative. X squared derivative is 2x. The derivative 2 to the power x is ln2 times 2 to the power x. Derivative 1 is 0. And then this is still infinity. Plug in infinity, still infinity form. Both top and bottom are differentiable, continuous. So use L'Hopital's rule again. Infinity or infinity form. So you got 2, then you get an ln, you got another ln 2, and still 2 to the power x. Now you can tell this one equals 0. Since this function, when x goes to infinity, this function converges to 0. So now I also have, because of the theorem I have here, because of this theorem, okay, because of this theorem, if your function f of x converges to L, then the sequence also converges to L. Okay, they have the same form. You change the n into x. So we got, therefore, the limit n goes to infinity, n squared 2n minus 1 equals 0. So we're done here. If you look at from the picture, x equals 1, it's 1 over 2 is 1. X equals 0, so it cannot go to 0. Okay, so the sequence is pretty much like this: 1, 2, 3, 4, 5. You see the sequence? The sequence only have this point, but the function will have a continuous line. It's decreasing, but both the sequence both the sequence and the line converge to the same point, 0. Does it make sense? Okay. So now I would like you to try another example by yourself. Find the limits of an equals n square plus 2n 3n square plus 3m as n goes to infinity. Can you finish this one? Okay, I think it's pretty simple one, right? You can use 2 ways to do it. First, you can do the traditional way we did before. I mean, you know that n goes to infinity, and n squared plus 2n, 3n squared plus 3n. The traditional way we did before this class, we can do n goes to infinity. We divide the top and the bottom by n squared, so it's 1 plus 2 over n. And 3 divided by n squared, 3n squared is 3 plus 3 over n. Well, n goes to infinity. You know, n goes to infinity, this is 0, so the final answer is 1/3. Make sense? This is before we learn the L'Hopital's rule, we do this. But now if we learn the L'Hopital's rule, you can also do another way. Given function f of x is x squared plus 2x, 3x squared plus 3x. What do you do? X is r. You can find the limit as x goes to infinity, fx. So this equals limit x goes to infinity. Because this is a continuous function, infinity over infinity form, plug in. So you can take the derivative at the top is 2x plus 2. Derivative at the bottom is 6x plus 3. Now it's still infinity over infinity form. So you use the L'Hopital's rule again. You get x goes to infinity. That is going to be 6 over 2. Sorry, 2 over 6. And equals 1/3. Okay. Since this function converges to 1/3, so I got the an equals n squared plus 2n, 3n squared plus 3n, or this equals 1/3 as well. So you can use either way, this way or this way. Sometimes this is probably you just do this. This is much simpler. But sometimes you have to use the L'Hopital's rule to do it. Okay, either one of these two will be okay to find the limit of the sequence. So far so good, everyone? Yes? Okay.
What does the r value stand for when you set x going to r right there?
Oh, this is just a domain of x. X be a real number.
Okay.
Yeah, x is the real number domain. We're not considering x equals a plus bi, like complex numbers. We're talking about here x is a real number. That means x is a real number. Make sense? Okay.
Okay. Yep. Thank you.
Okay. All right. So theorem 9.2. I just do a little bit more on the theorem, but it's just a very straightforward theorem. Okay, so if you have limit, let limit n goes to infinity an equals L, and the limit n goes to infinity, bn equals k. So basically we have two sequence. Okay, both sequence will converge. One of the sequence converge to L, the other sequence converge to k. Okay, so how about you add those two sequences together? The first one, limit n goes to infinity, an plus or minus bn equals. Can anyone tell me what do you think the sequence will converge to? Matthew, what do you think? If an converges to L, bn converges to k, and they an plus or minus bn, what do you think they converge to?
It'd either be L minus K or L plus K.
Yeah, L plus or minus k. Okay, so that's pretty straightforward thing, right? Okay, so second one, limit n goes to infinity, c times an. Since an converges to L, so limit n goes to infinity, c times an. So what does this one converge? I'll ask another student. Tell me. Okay. Eric, what does this one converge to?
C times L.
C times L. Very good. And C is a real number. Okay. And the next one, limit n goes to infinity, an multiplied by bn. So an goes to L, bn goes to k, an times bn. I want to call another student to help me. Bella, could you please help me with this one?
L times K.
L times k. Very good. Thank you very much, Bella. So you got this is L times k. The number 4. Okay, limit n goes to infinity. Okay, an over bn. So this will equals what? I think. Luke, can you help me with this one?
Would you go L over K?
L over k. Very good. Okay, so do you think is there any restriction on this one?
K can't equal 0.
K cannot equal 0. Very good. So bn not equal 0. So k not equal 0. Okay. So because if you put the denominator, k cannot be 0. That's very good. I think this theorem is very straightforward. That's why I think I can ask you can tell me. Okay. So another theorem or property, sequence theorem. If limit n goes to infinity, an equals L, equals limit n goes to infinity, bn. So an converts to L, bn converts to L. For example, 1 over n, 1 over 2n, right? Both converge to 0. That makes sense, right? You can have a sequence, for example, 1 over n, another one 1 over 2n. Both of them converges to 0. So if n goes to infinity, both of them converge to 0. Both of them converge to 0. That makes sense on this one, right? an and bn both converge to the same point. Okay, and if both of them converge to the same L, and there exists a integer n such that an less than equal to cn less than equal to bn for all n bigger than n, then the limit of n goes to infinity, cn equals L as well. So after a certain point, cn is between an and bn. and both AN and BN converge to the same point, then CN will converge to the same point as well. If I can draw a picture. No, if I draw a picture, it says AN is less than BN. So for example, this is BN. Okay. Now I have AN is less than. So n goes to infinity still. Suppose this is AN. You know that AN is less than BN. Well, after a certain point, for example, I probably can draw a little bit longer. Oh, this one is blue. Okay, it doesn't matter what this between them. What it doesn't matter what this is. Okay, but after one point, it doesn't matter what before this point. The Cn, the green one is Cn. Okay, the green one is Cn. So it doesn't matter what happened on the between this certain point. But after one point, for example, after this point, okay, after this point, then Cn is between AN and BN. Cn is in between. Since both AN and BN converge to the same point L, then Cn will also converge to the same point L. Does that make sense, everyone? Okay. Makes sense, right? Since in the end they all go to the same point. After one certain point n, after one certain integer or certain term n, then all three will converge to the same point. But Cn is between AN and BN. We know that AN and BN converge to the same point. Okay, let's look at an example. Example, less than AN, less than that. Okay. Let's look at one example. So AN equals 1 times 3 times 5 times 2n minus 1. So top is multiplying all the odd numbers. The bottom is 2n raised up to the power n. Okay. So if I write it out, I got AN. If I write it like separately, I got 1 over 2n times 3 over 2n times 5 over 2n multiplied by 7 over 2n. Continue. 2n minus 1 over 2n. That makes sense, right, everyone? Yes? Okay. So now, I want to find out what is the limit n goes to infinity AN. N goes to infinity AN. Well, n here, you know, n is a positive integer, right? N is a positive integer. So can anyone tell me what do you think the limit AN is? Just a guess.
Maybe 0.
Maybe 0. That's a very good guess, actually. So why do you think it's 0, Lacey?
I think if we kind of differentiate the first part, we get rid of the n
Okay.
after the first step, and then we're still gonna have like n at the bottom.
Okay.
So that's like 1 over infinity.
Okay. So if you use that product rule, because you can do it. You can use the x is 2x minus 1, but it's just too hard. It's very complicated to write everything out. You can have a quick estimation of using L'Hopital's rule. You assume you have x, fx equals 1 times 3 times 5 until the last one is 2x minus 1. Okay, the bottom you can do 2x to the power x. Okay. But if you take the derivative of this one, this is a very complicated one because you have 2x minus 1 The previous one is 2x minus 3. You're going to have a lot of products of x. Okay, the bottom always exists, that's true. But it's hard to do the L'Hopital's rule on this to take the derivative. Although it is infinity over infinity form, okay, but it's not so easy to do that. But you get a quick estimation, that's right. So now, what I do, I want you to tell me, I want to compare an 1 over 2n. Which one is bigger, which one is smaller? Just compare an and 1 over 2n. Can you tell me?
an is bigger.
An is bigger. Lacey said an is bigger. Can you tell me? Is an bigger than 1 over 2n? Is that what? Compare an and 1 over 2n. Which one is bigger? Fair? What do you think? Well, we just compare a and b, and we're not considering n goes to infinity, because n goes to infinity both will go to the same place. Now we just can consider compare an, compare this one 1 over 2n times 3 over 2n times continue 2n minus 1 over 2n. Compare this one and the 1 over 2n. Compare this two. Compare this one and this one. Not just n goes to infinity. Which one?
An will be smaller.
Why is an smaller?
Because if we're gonna have like the n term, it's gonna be a really large number, and they're like the same numerator for them.
Okay, so any other straightforward idea? Tell me why is an less than 1 over 2n?
In the first fractions there, we're going to keep multiplying by another fraction, which is just going to keep making the value smaller and smaller.
Very good, Taylor. Thank you very much. Your first one is 1 over 2n. Compare this one and this one is the same thing. But we are multiplying by a fraction. For example, this one is 3 over 2 times 3 is 4. Multiplied by 5 over 6. You're keeping multiply a number. Keep multiply by a fraction which is less than 1. You multiply 2 4/3, all of these numbers are less than 1. So you actually making that number smaller. That makes sense, right? If you use 2 times 1/2 is 1. So you multiply by a fraction which is smaller than 1, that makes the whole thing is less than itself before, because multiply a smaller number than 1, right? A number less than 1. So now we compare an is less than 1 over 2n. That's perfect. Now I want to compare an and 0. Which one is bigger? N is a positive integer.
An is bigger.
An is bigger. Why is an is bigger?
Well, no matter what value we put in, it's always going to be above 0.
Yes, well, no matter whatever number you put in the sequence here, you always make this one bigger than 0 for sure, because n is positive. No matter how many integers, how many fractions, positive times positive times positive, it always give you positive. As long as it's positive, it's always bigger than 0. So now I have an is less than 1 over 2n, but it's bigger than 0. And we can tell that limit n goes to infinity 1 over 2n. That's a very obvious thing. You can tell me what's the limit of an 1 over 2n. What's the limit at 1 over 2n?
0.
0. Very good. Because infinity plug in is 0. Thank you, Taylor. So you plug 0 into 1 over 0 equals 0. Now I got an is a sequence. It's between 0, bigger than 0, less than 0 when n goes to infinity. Now it's in between 0 and 0, so it itself will go to 0 as well. Does it make sense? So you use this theorem. So 1 over 2n, limit of 1 over 2n equals 0, and an is bigger than 0. Now I got from the sequence theorem, I got n goes to infinity, an is also 0. Because if n goes to infinity, the 1 over 2n goes to 0. You can tell that 0 less than an less than 2. You got a 0 here, you got a 0 here, n goes to infinity. So middle one must be a 0. Does it make sense, everyone? Yes? It doesn't make sense, right? Okay, a number is bigger than 0, but it converges to 0. It converges to 0, okay? So an is bigger than 0, less than 1 over 2n. But 1 over 2n converges to 0. So an must converge to 0 too. Okay? That makes sense, right? So this is the same idea as we have here. Okay? So basically, if you draw a picture, if you draw the picture of this one, you can tell, well, 1 over 2n is pretty much like this. Now you have this one, n goes to infinity, converge to 0. So this is 1 over 2n. For example, this is 1 over 2n. Now the another one is less than 1 over 2n. So it's always less than. So it's always between 1 over 2n to x-axis. X-axis. Now you can tell 1 over 2n converge to 0. The blue one always will also converge to 0 as well, because it's bigger than 0. It only converges to 0. It's always between 0 and 1 over 2n. So if 1 over 2n converges to 0, then the sequence will converge to 0 as well. That makes sense, right? Okay. So next one, for the sequence an, if limit n goes to infinity, an equals 0. If the absolute value of an equals 0, then n goes to infinity, so then limit n goes to infinity, an will equal 0. If you add absolute value on the sequence, it goes to 0, then the sequence itself goes to 0 as well. Why is it like that? Because if it's a negative, you add absolute value is positive, it goes to 0. It will go to 0 as well, itself. No matter if it's positive, it goes to 0. If it's negative, it converges to 0 as well. That makes sense, right? Okay. All right. You kind of like if an is positive, now you don't have to change anything. Limit n goes to infinity, an just equals limit n goes to infinity, absolute value of an will equal 0. If an is less than 0, it does not matter, because you can take it. You have a limit of n goes to infinity, an will equals negative limit n goes to infinity of an, absolute value, because it's negative. Now this is positive, add negative is negative. So since this is 0, so the negative 0 is still 0. That makes sense, right? It's just a very simple proof. Now let's look at an example. If an equals negative 1 to power n times 1 over n. So what I have here, an will be negative 1, positive 1/2, negative 1/3, positive 1/4, negative 1 over 5. So continue. This is the sequence. Okay. So I want to find the limit of this one. What I can do? Can anyone tell me what the absolute value of an is? I'll just do this one very quick. You add an absolute value, the negative to power n, negative 1 to power n, what goes away is just the 1 over n. Make sense, everyone? Okay. So you have this is just 1 over n. I know that limit n goes to infinity, an equals limit n goes to infinity 1 over n goes to infinity, so this equals 0 for sure. And also, then from the theorem I got a limit n goes to infinity an equals -1 to the power n times 1 over n also equals 0. Because the absolute value converges to 0, so the self also converges to 0 as well. Okay, so I think I'm going to stop here today, and tomorrow we're going to finish this sequence. Just one more theorem, and then we can continue a little bit more on section 9.2, series and convergence. Okay, sequence, we're looking at one term, an. Series is summation of the sequence. Okay, that's what we're going to cover tomorrow. And if you have questions, just feel free to email me. All right, and